Hello, in this example we want to go through how do we find the domain of certain kinds of functions, namely polynomials, rational functions, and radical functions. The first thing to know about finding the domain of a function is that we must exclude any value of x that results in a non-real value for y. Remember, we define the domain as the set of all values of x in the function that result in some real value for y. For functions like a, which is a polynomial, we can really say that there is no set of values that would result in a non-real value for x. So in this case, for all polynomials, we can pretty much state outright that the domain is going to consist of all reals. Now, we can state that as one of two ways. Generally speaking, either we can state that x is in the set as an element of the set of real numbers in this fashion, or we can use interval notation. In interval notation, the statement for all real numbers looks like x in an element of the set from negative infinity to positive infinity. Well, this is helpful because, of course, we know that anytime we run into a polynomial, that's going to be our domain. Now, the situation changes when we talk about a rational function like g of x right here. G of x is a function whose domain is defined by the denominator. And in this case, in a rational function, the denominator cannot equal 0. So we need to find any values of x that is going to make that denominator actually equal to 0. So we cannot equal 0. So in this case, let's find where the denominator actually does equal 0. So we're going to set x squared minus 9 equal to 0 and solve for that set. Well, this is a pretty direct one. We can factor, or we can use the square root principle. Either way, x minus 3 times x plus 3 is equal to 0, meaning that either x equals 3 or x equals negative 3 cannot be included. So we're going to exclude them from the set. And so we would write for our domain one of two things. In set notation, in the set builder notation, we'd write, well, the set of all x such that x does not equal plus or minus 3, a very compact kind of notation right there. But we can also write it in interval notation this way. We can say the set of all real numbers that start at negative infinity and go up to negative 3. We exclude negative 3, and we take the set of all numbers between negative 3 and positive 3. We again exclude positive 3 and take the union of that set with 3 to positive infinity. A little bit longer, but says the same thing. Finally, in the last case right here, whenever we're dealing with a radical, we have to recognize that in a radical, the radicand cannot be negative. So we must exclude any numbers that is going to make the radicand less than 0. So what should we do? In this case, what we're going to do is we're going to solve an inequality. We set it up, the inequality, as 16 minus x squared is greater than or equal to 0. If we find all of those values, we find the values that are actually in the domain. This is going to be a case where we can solve the inequality by using the critical number method. The critical number method says that we factor the expression on the left side of our inequality. In this case, erase that here. In this case, the difference of two squares, 16 minus x squared, turns into 4 minus x times 4 plus x. And so our critical numbers occur at x equals 4 and x equals negative 4. X equals negative 4, x equals 4. So on a number line, we can set up two critical points, one at negative 4, one at positive 4, and we can make a sign graph. The way we make the sign graph is that we look at each factor individually. If we take 4 minus x, we find that the factor 4 minus x is always a positive number. If we include numbers that are less than negative 4, for example, 4 minus negative 5 would be positive 9. And it would be positive if we include any numbers less than positive 4. So, for example, we subtract 4 minus 1, we'd also get a positive number, but we get negative numbers for all values to the right of 4. Then we examine the factor 4 plus x, and again, we can say that, well, if we substitute in a number that's less than negative 4, we're going to get a negative value, but if we substitute in a value greater than negative 4, we get a positive value. Remembering that we're multiplying the factor 4 minus x times 4 plus x, we're going to get a negative, a positive, and a negative over each of these intervals. We want the one that x is greater than or possibly equal to 0, so we're going to include all numbers on the number line, including the endpoints between negative 4 and positive 4. In interval notation, this is very simple to write. We say that in interval notation, the domain is the set of all x included in the set from negative 4 to positive 4 with square brackets around our endpoints. In set builder notation, we could also write a very similar domain. We're going to write the domain of all x such that x is between negative 4 and positive 4 using this double inequality symbol. Those are the domains that we wanted, so we're done.